Professor Sergio Albeverio with the talk From the Heat to the Schrodinger Equation and Quantum Fields. This is the talk dedicated to the memory of Oleg Smolyanov. So Sergio, please.
Thank you very much, Jana, and thank you very much to all organizers, and a special thank to Sonia, who helped me with the technical productions of these slides, and of course, also in many of the things I will tell you today. This morning we heard already the presentation of Oleg Georgievich Smolyanov's work by beautiful presentation by Vladimir Bogachev. And so maybe I short a little bit this part because there is some overlap, but here is the outline. First was something like this, and the common path with Smolyanov, and then something about its McGriff Schrodinger group, which we heard also very much here, and also this will be short, but I'm concentrating on the passage to from finite dimension to quantum fields, which of course is a big jump, but I tried to make some condensated presentation. And of course, this was also a topic which interested very much Oleg Smolyanov. And then a final remark on stochastic quantization equation. This is about some new development. Stochastic quantization equation, so SPDs as a constructed tool. It's quite new. In recent years, let us say. So now it's about Smolyanov. This was already said this morning, and everybody knows here. And early work it's here was also recalled this morning. Surface measures are very important also. His work also in recent times. But here is what I will mainly concentrate is topic related to infinite dimensional integration, function integration, both in the probabilistic setting and the Feynman path setting. And this, so to say, was one reason of our common path coming together. Then he made work on infinite dimensional Lebesgue measure, also a topic in this connection, and these are the two topics. And mathematical physics, of course. The books were recalled already this morning, especially the one with Professor Shavgulidze on path integral was mentioned also by Sonia. This would be, it was one of our common points, and unfortunately now we cannot pursue those, but somehow these two communities of probability and oscillator integrals, if Feynman path, if you like, parabolic, elliptic problems and hyperbolic should come closer together. And I think now it is a good time for that too. Probabilistic infinite dimensional integrals were on the interest, one of the main interests of Professor Smolyanov, especially after the 90s. And I had the luck to come to know him even before, most probably, but it's certainly in the 90s, there was I might say, rather continuous flow of co-workers and exchange and cooperation on many levels and fronts. Vladimir Bogachev, Andrei Krenikov, they came to Bielefeld, Bonn, Bochum, Bonn. Evgeny Shavgulidze, we shared at least one paper. Jana, we met, and of course we talked about our common relations to Oleg, and in Kaiserslautern we met. And we met also with Oleg at many places, which I cannot even remember all, but certainly the places where I was acting in Bochum, Bonn, and then there were many conferences in Bielefeld, Madeira, Trento, Levi, probably also in Swansea, where we met, and also the co-workers, and especially Sonia Mazzucchi became also joint co-worker. She has been long time, has been my student, and her work on oscillator integral has been quite determinating in all I did in that area. We had 12 joint publications with Oleg Smolyanov, direct publication, so to say, where both our names are on. I just put the keywords here. You see there are from Schrodinger to probability, but quantum systems were quite central. And also polynomial potentials, stochastic differential equations. There is one maybe which is less known. It is the paper by Oleg together with Dara Neat and Toby Truman. This is on a model on the Burgers-Zeldovich model is called for the formation of planetesimals via Nelson stochastic mechanics. It's a very nice paper, appeared in 2012, and they give us the, so to say, honor to having continued our initiated some work in this direction by considering the Titius-Bode law and the orbits of planets and satellites, connecting them somehow with the orbits of hydrogen atoms. But there is an interpretation, but for this. And then that approach, so to say, from 83, combined with the equations of Burgers, Zeldovich, and Shandarin about the stratified structure of universe, connects to probability, and this nice paper gives, so to say, more dynamical insight about this phenomenon, which was just kind of postulated in our original work. So let me just say a few words more personal to Oleg. He was an excellent mathematician and a human person, and we became very close friends. I have very good memories of our meetings. Unfortunately, as I said, a little confused maybe also at the beginning, but for sure, for many years, decades, we were, I have memories, and he was very kind, cheerful, and it was always a very great pleasure for me to communicate with him. And also we exchanged calls whenever he was traveling. Now it may also discussing our coming meetings. And now it is no longer possible, but memories, as I said this morning, are a stay. He left an impressive, long-lasting scientific and human heritage. And we have this conference is a testimony of this. Now let me go over to a topic which, as I said, connects to interests of Oleg, even if not directly, all parts of it, maybe not directly to what he has been studying, but for sure he was interested in quantum mechanics and quantum fields. And I will now give a presentation which is aimed at arriving at quantum fields. And instead of looking at particles, better to look at oscillators, thinking of classical harmonic oscillators like it is here. sorry, I don't manage. Okay, this equation there. And if you make it quantum, you use the Hamiltonian, which is not just the minus the Laplacian itself, but it is plus x squared, which has to do with the harmonic oscillator, and this minus 1/2, which makes the lowest energy to be 0. This came in, the problem of this 1/2 came in the talk by Professor Chamar of this morning. And this is an operator in L2. And then you have a semi-group, the heat semi. I call this still heat semi-group, but it is with this potential term is square, quadratic, and by it is even an analytic semi-group. The spectrum is discrete in this one. Finite dimensional case, if you make analytic continuation, you come to the Schrodinger group, which is quantum mechanics proper. And the important is the quantum mechanical position operator at time 0 is transformed by the unitary group in the quantum mechanical, so to say, value of the quantum harmonic oscillator at time t. 0 to t is made by the unitary group. Now, we have some interest in changing dx, Lebesgue measure, by some probability measure, because, as was pointed out this morning, when one has infinitely many oscillators, one can do as was proposed this morning, but another possibility is to have in advance, or to say, a presentation of the harmonic oscillator via a probability measure. And this is possible exploiting the L2 space with respect to Lebesgue measure is a unitary equivalent by the simple multiplication of functions by this omega function here to an L2 space with respect to the probability measure. This is only finite, it's only sigma additive, it's only sigma finite, but mu 0 is really probability measure. This is the ground state function. And if you have a unitary map from one Hilbert space to the other, operators in one space go over to operators in the other space by unity equivalence. And if the origin operator is self-adjoint, realized, the target operator is also self-adjointly realized. And in fact, here is a unique self-adjoint extension of the right-hand side here of this, which is called maybe diffusion operator, because it is Laplacian plus a drift with a drift. This H mu 0 is a realization, the closure of the restriction of this operator to in L2 with respect to mu 0 is the new Hamiltonian. Then this generates a symmetric Markov semigroup, so positivity preserving and contracting in the always now in the L2 space with respect to probability measure. And it is the so-called Ornstein-Uhlenbeck velocity process, which is a linear drift and a Brownian motion. Then you use this to, when this process, this Brownian, this Ornstein-Uhlenbeck is started with invariant measure, it has a covariance, it is Gaussian, the measure is Gaussian, so it is Gaussian, and it is on path space, the measure on path space has this covariance here, which is given by this is just a name of covariance at times T1, T2. So it's the 2 times correlation of the process. And it is here simple because one can compute it. And And I wrote it, it is called S2 because later on this will be called Schrodinger function, and this is the 2-point function, so to say, of the one-dimensional space quantum fields, space here being the values of the oscillator. The past space distribution is this one, which has this covariance when you do concrete. So it's a Gaussian measure now on an infinite past space, so it's infinite dimensional space. And it has, actually you can take it as a continuous function in here in case, because you have the one dimensional. You see from the covariance is a nice covariance. So this is a past space measure, and for normal distribution, which means 0 and this covariance here. It is the fundamental solution of the second derivative. Then, what about the quantum harmonic oscillator? You come to it, well, first of all, from quantum mechanics, you know that, well, there is interest in at least to find correlation of the evolution of this quantum mechanical oscillator at 2 different times. And the correlation are usually taken in the Hilbert space. And if this is a real, which is the Hilbert space is usually taken to be this omega, which is given by this vector omega, which is the ground state of the quantum harmonic oscillator. This is called the Weidmann function. And now by analytic continuation, you can represent these quantities by analytic continuation from this Schrodinger function by making the time imaginary. This is the one connected with the semi-group e to the minus th mu. Now, if you have the picture, the Dirichlet picture, I call this Dirichlet picture with a reference measure mu0 instead of Lebesgue measure, then you come to correlation which are given by the corresponding or the heat semi-group given by mu0. Sorry, I have to drink it. Sorry. Analytic continuation in time. So instead of e to the minus t h mu0, which is a contracture semi-group, you take a unitary group e to the ith mu0, and that is what you can represent in here. And if similarly, if you take n times, you have such correlation functions, because essentially we are in the Gaussian situation, so they are expressible by 2-point functions, by 2 correlation. Now, what about perturbation? So it was said in many times this morning and this afternoon, Feynman-Katz formula. You have a Feynman-Katz formula also for going to the unitary, to the quantum mechanical picture by analytic continuation using the measure mu, and this was the past space measure I was considering. And you put up, at least formally, you put up such a Feynman-Katz vector. You have an infinite, V is a nice function. The potential term is supposed to be nice here. And then, but even here you have maybe a little problem because you have the whole line you're supposed to take because you are on the full space. But this can be done by taking limit. First you take a finite interval and then you make weak convergence. And you come from the probabilistic side, then you have this object is a probabilistic object, and you have an analytic continuation. You come to the quantum mechanical situation. Now let me go over to the case of quantum fields. What are quantum fields? Of course, this is a long story I cannot go into, but I just stress the first, there are scalar fields, which I take different from other talks this morning. Scalar fields. These are analogs of infinite, they are infinite dimensional oscillator equation, if you like, but with a potential term, a quadratic, with this term. And so it is this wave equation, but with a linear term. And this is the D'Alembert operator. And so the underlying space is, well, here there is a printing error. T is on the real line, X is on the Euclidean space, sigma dimensional Euclidean space. But of course, when I think of relativistic, I should write Minkowski space rather than Euclidean space. So for the quantum harmonic oscillator, we had a description by measures, mu0. You remember this was just the equivalent of Lebesgue measure, the replacement for Lebesgue measure. And then we have the path-space measure and the associated Einstein-Uhlenbeck process. Now, when we take the quantum free field, the replacement now are mu0 should be replaced by something that you can actually guess by looking at the equation, because it's like an oscillator, because it has secondary, the classic equation, it has second derivative with respect to time, but if you bring the Laplacian here to the right-hand side, it's like you would have such operator on the right-hand side. And so the correct choice of mu0 is this one. Of course, you have to discuss this. I don't have time here to make it, but so that is our replacement for mu0. The replacement for the path-space measure, it's a simple computation. Then to see, this is Nelson's measure, which is the Gaussian distribution with mean zero and covariance, this operator here. So here is -1/2, this is -1, this is called Nelson's free field measure. And what is the analog of what I call for the harmonic oscillator Q quantum mechanical? Here is, and what is the analog of the Einstein-Uhlenbeck process? This is first the Einstein-Uhlenbeck process, is a process xt, which is denoted also by phi, or usually is denoted by phi. And now one can look at this as a random field in function of time, t, and space. And this is now in Euclidean space-time, RD, really. Then one can take, this is an infinite dimensional Einstein-Uhlenbeck process, and it is singular, but never mind, it is well realized, for instance, on distributions, tempered distributions. You take the expectation, and this gives the Schwinger functions. They exist, the expectation, they give the Schwinger functions of the quantum, the Euclidean quantum fields. And by analytic continuation, which is possible because after all, this Einstein-Uhlenbeck is again described by Dirichlet form. The proper theory here would be Dirichlet form, and this gives the relativistic picture, because then after analytic continuation, this becomes invariant under the Lorentz group, Minkowski group. Now, of course, one is more interested in interactions, and this is, again, a long story, and there was a lot of work to do this. It's not trivial, because Nelson measure has a bad support, as I said. I mean, you see this fundamental solution of that second order operator. If you compute it, you see that that's as a kernel, which is singular on the diagonal. And it is, so you can realize on distribution, not on functions. Then you would like to make, following the procedure for the harmonic oscillator, you would like to make a Feynman-Katz formula, but you don't know what it is. V which appears in the equation, in a classic equation, what is V composed with the distribution, because it's a function composed with the distribution. And then, so to say, not to talk about that you have to integrate for over space. So this is so-called V-phi2 heuristic representation of the model. Therefore, this.
Sorry, Sergio, you have 1 minute more.
Oh God, sorry. Well, you're right. So I make the the story short. You have to go down in dimension, because if you stay up in dimension, this approach and other approaches that I know don't work. But for dimension 2 and 3, that means just one dimension less than the 4 space-time dimension of physics, then you can do such models. And this is part of constructive field theory. There are many books and survey paper. And I come probably now to the last minute, well, less than a minute now, the recent approach, because so to say, this approach, constructive quantum field theory, has been very well developed by pioneers who are also partly represented in books, and the models work. You need to do renormalization. You need to do a lot of work to construct this picture. But yeah, a lot of work. And since at least some of our interest, also sharing with persons here, is also stochastic, the idea came to use more stochastic directly, so to say, to make so to say, an alternative construction of the limit measure just by stochastic means, without using tools coming from maybe, yeah, partly statistical mechanism you consider also stochastic, but here is more stochastic analysis, so to say. And this is to look at such an equation, such an equation in stochastic PDEs, where little x is space-time, the Euclidean one, and tau is an additional computer time. This suggestion to look at such equations and then find the invariant measure goes back to Parisi this year Nobel Prize, and Wu in 81. Heuristically, you can see that this is, indeed, if you compute the invariant measure associated with this stochastic quantization equation, is just the measure which was written heuristically. Now, the new news is that stochastic quantization can be made mathematically the full program. So it was, of course, around pioneer work by, after suggestion by people like Ferris Lazzino, Da Prato and co-workers, and especially the paper by Da Prato de Buch was quite explosive in this action, in the sense that it was the new idea of constructing, at least on the tour, strong solutions of that equation using a trick which is called now the Prato de Buch trick, which is splitting up the, so to say, you make some regularization, you split up the solution, the would-be solution process into one part, which is the Ornstein-Uhlenbeck part, and another part, and then you make many estimates using using match analysis. Entirely, the Gubinelli was determinating also, because they gave the impulse to construct 543, at least first on a torus, and first local in time, then globally, and then the last steps were by Gubinelli of Manova and other, but I want maybe to take this more recent one, and Kusuoka and Barashkov and Gubinelli, and some cooperation in Bonn and Japan also. this is about these models have been, but so to say, what is new now is that the progress has been done from the original, is so to say, as a constructive tool. So the measure now is a self-constructed, so to say, self-contained construction of the invariant measure. And some properties, for instance, that is not Gaussian, that it is reflection positive, so you can do analytic continuation. What still something meeting in this sort of alternative? So we are, so to say, still not.
Sergio, I'm sorry, we have no time for
I just
discussion.
wanted to say that what is missing is one either translation invariant or rotation invariant, and the uniqueness, which would give identification with other constructions. Sorry to have taken too much time.
No, I guess the time which is given to you is too small, I would say. So probably next year.
No, it is my fault.
Probably next year you will give a 1 hour talk. Sorry, we have no time for questions, but probably after all the talks, we can stay for a while and discuss.
Yeah, I would be happy after the talks.
Yeah, so now please unshare your screen. And thank you very much for your talk.
Recording stopped.
No, thank you very much. Thank you for your patience.